So the world was just coming online, just coming of age. And there were no smartphones. There weren't even Palm Pilots. Like, the people having devices in their hands was not a thing. If you walked up to somebody on the street and said, hey, do you have a phone? They'd look at you funny. So a young William Clinton just completed 1 year as the President of the United States, and Green Day just released Dookie. And the Winter Olympics were held in Lillehammer, Norway, and The Lion King came out that year. Friends was in its first season, and the game everyone was playing was Doom 2. These were heady days indeed. And in these halcyon days, Microsoft released a preview of the next generation of its Windows operating system, codenamed Chicago. The World Wide Web was just beginning to become a thing. And you could, most people didn't have it in their house. You could walk down to an internet cafe where you could exhaust the internet in a couple of hours, by searching on web crawler through Mosaic. So yeah, the PlayStation came out that year. That was state of the art in computing. And the Commodore International went bankrupt. And the latest and greatest in computing was the Power Macintosh. And as we know, RISC architecture changed everything. Steve Jobs was not at Apple. He was at Next, selling object technology and Objective-C to eager customers. And a company called Rational Software was developing the first seeds of a unified modeling language called UML, which was to become the lingua franca of object-oriented design. So speaking of object-oriented design, so this book came out, right? Design Patterns, Elements of Reusable Object-Oriented Software. So this was published in 1994, 20 years ago. So it was written by the so-called Gang of Four, and the idea with this book was to apply. Here, I'll hold it. So it was to apply the idea of pattern languages, which comes from architecture. An architect named Christopher Alexander developed this idea of pattern languages in architecture. And so the idea of this book was to apply that to software creation. And this idea caught on like wildfire. And it actually popularized the notion of software architecture. That was not really a thing, at least it wasn't a very popular notion, before this book. And so this became the Bible of self-styled software architects everywhere. So, the book contains classic object-oriented design patterns that I'm sure we've all heard of. Hits like Abstract Factory and Prototype. Iterator is in the standard Scala library. Singleton is actually built into Scala, right? Yeah! And, you can, people combine these things. You can have Abstract Singleton Prosy Factory Bean in your library, and people are like, yeah, that's awesome. But a lesser known pattern is the interpreter pattern. This one is sort of like an unsung hero. So the description of interpreter, if you would all turn to page 243 in your Gang of Four books, you can see that the description is that given a language, we define a representation for its grammar along with an interpreter that uses the representation to interpret sentences in the language. Right? Sounds kind of weird, right? And so it was kind of a misunderstood pattern, and people didn't really get it. For instance, odesign.com now says the interpreter is one of the design patterns published in the Gang of Four, which is not really used. And the department chair of computer science at San Jose State University said, I'm not sure this pattern has wide applicability. And Steve Yege, in one of his rants, I'll just read this out. Of course I loved all of design patterns, except for pages 243 to 256, which is the interpreter pattern, which had the magic property of inducing a coma-like trance whenever I tried to skim through them. I could put on a black ninja suit and sneak through the building, and presuming I didn't get arrested, I could tear those pages out of every single copy of design patterns at Amazon, and almost nobody would notice. But, so this is a quote from me. So somebody, caught me saying that at one point. So no, I really think that this pattern is underutilized, and it's sort of, it captures an idea that I think is extremely useful, and it's sort of universally applicable to almost everything. So let's look at this. Let's look at this pattern. So what is the interpreter pattern? Well, the motivation section says that so you have a problem that occurs often. You express instances of the problem as sentences in a simple language, and then you solve the problem by interpreting the sentences. Now they give an example in the beginning. They always start with an example in this book. And so the example that they start with is a simple regular expression language. So the problem is that you want to search for strings that match a pattern. And then you have regular expressions, which are sort of a language. And then you interpret those expressions using an interpreter to match actual strings. So here's the grammar for their regular expression language. So they start with, an expression is one of these things. It's a literal or an alternation or a sequence or a repetition or another expression in parentheses. An alternation is two expressions separated by a pipe. A sequence is two expressions separated by an ampersand, and a repetition is an expression followed by an asterisk. And then a literal expression is a sequence of characters. So here's the UML diagram for that. I'm sure all of you are well versed in UML by now. So it's totally clear, right? You have a superclass, which is abstract. And then you have 4 subclasses, right? And the subclasses contain instances of the superclass. Like sequence expression has 2, alternation expression has 2, repetition has 1, right? And so you have this abstract class, and then you have these subclasses, which are sort of the instances. The cases. So in Scala, we can do it like this, right? So we can have a regular expression trait, so that's abstract, and then we have case classes for each one of those. But that's a little verbose for me, so I'm just going to do this. So we have a sealed trait expression, and then we have a case class for each of the rules in the grammar. One for literals, one for and, which is the sequence expression, one for star, which is many, and then or, which is the pipe. Okay, and then an actual expression in this language has this structure. This is the UML structure diagram for one of those things. And so if you have an expression that represents a structure that represents a regular expression that matches strings that start with raining and then are followed by many instances of either dogs or cats, then this would be the expression for that. And in Scala, it looks like this. So it's just an and containing a literal and a many of an or that has 2 literals, dogs and cats, right? So then the idea is that we can interpret these expressions given a string. We interpret them to see if they match that string or not. So the idea is then, given a string, if you have a literal, then you just check if the literal string matches the input string, and then or checks if either one of its sub-expressions matches, and checks if both of them match in sequence, and many, tries to repeatedly apply the pattern. So here is an implementation of the interpreter for regular expressions. Now, they don't actually give the implementation until late in the chapter, and because they use a mutable context, so they pass in, instead of passing just the string, they also pass in a mutable context, and the interpreter proceeds to mutate it. And it's all written in Smalltalk, and it's totally awesome. But it's very long. But I wrote it out in Scala using an immutable state. So you just pass in the input string, and then it returns the resulting string. And what this does is, if there's a literal, then if that literal starts with L, then it matches, and then we drop we consume that bit of the string. And then and, or, and many actually recurse over the structure and pass the string along as it's being consumed. So it's a purely functional thing. In fact, we can use the state monad. We can use like from Scala Z state. So our interpreter that just takes a string and returns a Boolean and a string is actually a state machine. So we can make that explicit using Scala Z's state monad. In fact, they say in the book on page 245, they say that you're encouraged to not actually interpret using a context. They actually encourage using an immutable interpreter, so an actual state machine, right? Which is what I've done on the previous slide. So yeah, they say interpreters are usually not implemented by interpreting parse trees directly, but by first translating them into another form. For example, regular expressions are often translated into state machines. So, some important things to note. Expressions are pure syntax. They're just syntactic. They don't have any intrinsic meaning of their own. Right? The fact that you see and, or, and many, the actual ascription of the meaning is not inherent in the syntax, is not in the objects. Semantics are given by interpreting in some context. We could interpret with a context that turns all the ands into ors. That would be perfectly valid. So an example of a translation of giving semantics to an expression is to translate it into a state machine. So then they give the overall structure of the interpreter pattern, which looks like this. And again, this should be totally clear, right? I just have to show this for 3 seconds. So you have a client that knows about some context, and then there's an interpreter that receives that context. And it consists of an abstract expression class, and then there's a number of subclasses. And here they just say that there are, in general, 2 different kinds. There could be a terminal expression, which is not recursive, and then a non-terminal expression, which is actually recursive, right? So this looks really familiar, right? So in Scala, we have a sealed trait and then a number of case classes, right? So interpreter is actually the algebraic data type pattern, right? So it's this closed system consisting of an abstract supertype and a number of case classes. And if we carry that thought further, we could say that algebraic data types actually are little languages. And then we have interpreters for sort of interpreting those languages. For example, option is a little language that has 2 instructions. So one of them is for specifying that there is an element of type A, and the other one is for specifying that there is not an element of type A. Right? So you have none and some. These are both terminal expressions in the pattern. So yeah, you take a problem that occurs often, which is the ability to say that there is the lack of a value. So that's what option does. And then you express instances of it as sentences in a simple language, that is in the option data type. And then you solve the problem by interpreting these sentences. So, but we'll get to what that means to actually interpret option. So again, option is purely syntactic, right? There is no inherent meaning ascribed to some and none, right? It's just some has a value of type A and none does not. But the actual option data type doesn't tell you anything about what that means, right? It's up to some interpretation in a context to then deconstruct and figure out what to do in the case that it's none or if it's some. So if we wanted to take the interpreter pattern very literally, then option would have a method like this. It would take a mutable context. It would just pass into option. And then the interpret method would proceed to mutate that context in a certain way. But then we'd have to have one method on option per behavior that we want, right? So we'd have to have a foo context and a bar context. And any type of context that we might want to work with option, we'd have to have an entirely new method. Well, fortunately, all of these interpreters are going to have a very similar structure. So what we have instead is a fold. So fold can be seen as the interpreter for option. You give it the meanings of the individual constructors for the none and the sum. So you're saying in the case of sum, turn this option into a B by just using the Z. And then in the case of none. And then in the case of sum, turn it into a B by using the function f. So you pass in handlers for each of the cases. And that's what it means to sort of interpret an option, to give it some semantics. So the astute listener will note that that is the visitor pattern, right? So we're actually passing in the Z and F objects actually constitute a visitor object. So if we were to implement the visitor pattern for option, then we'd have something like option visitor, and it would have 2 members. One of them would be, one of them would have the shape of F, and the other one would have It'd just be a sort of a default value to give in case of none. All right? But we can fold any ADT. We just need a handler for each case. So in our regular expression language, we can write many interpreters that all share the same structure by just passing in how we want to handle each of the cases. All right, so we can fold one of these regular expression things by just saying, well, how do we handle literals? How do we turn them into A's? And then how do we handle ands, and then many and or? And so it's recursive. So the only case that really turns something into an A is lit, right? We turn a literal string into an A, and all the other ones recurse over the structure using the inner A as the argument. Okay? So yeah, we have some other language A that we're turning this into. So in that structure, it didn't really matter that our literals were strings. They could have been any type, right? At least for the case of sort of the general fold. So instead of having an expression whose literals are strings, we just say, well, we have an expression whose literals are T of some type T. And then that works as long as we can turn our T's into the language or into the semantics A, that works out and the implementation is identical. Okay? But so the fold, so writing the general fold like this actually makes this pattern easier to see. Like we could have extracted some kind of general thing like this. Like we could have extracted the idea that the literals don't have to be strings, from the interpreter pattern somehow. But I think writing it, when you write out the fold like this, it becomes very obvious that the literals don't have to be strings. Okay, so what is folding really? So folding essentially replaces all the instructions in the program. So you have your expression language and you have some expression written in that language. And folding replaces all of those instructions with instructions that come from a different language. But that language has to have the same kind of structure, right? For example, we could fold our regular expressions. Let's say they were full of Booleans instead of strings. Then we could use it basically as a Boolean algebra. So then we could say that, folding a regular expression that is full of Booleans, passing in the identity for the literals, and then and for the sequence thing, and not instead of many. So we're saying that the meaning of many is actually not. And then we're saying that the meaning of the or thing is Boolean or. So the meaning of the structure isn't specified until we give it meaning by folding. So for example, using Booleans instead of strings. So they actually give this example in the book, right? So there's a fully worked example in C++, really, really long, hairy C++, so they go through this exercise of implementing a Boolean expression language, but it's totally separate from the string expression language that we used earlier. But it's very similar. It has a similar structure, right? So a Boolean expression is, an or, an and, a not, and they have variables, or they have, another Boolean expression. There's one case missing here, which should be constant. So it's either constant, true, or false. Okay. So then this example is slightly more enriched. So in addition to having the constants or the literals, true and false, they also have variables. So you could have variables that have names that look like strings. And then you can actually, the idea is that you should be able to interpret it and replace those variables with Booleans. Yeah. So you have a Boolean expression. Could be represented in Scala like this. So you have a literal Boolean, you have and, not, or, and then a var, which is a string. So that's just a variable name. And it's not specified what that means, right? What does it mean for there to be a string inside of this thing? So what they do, so the book talks about using different interpreters in this particular example. And they give implementations for each of these interpreters. But in the book, the two interpreters are almost identical. So they have two examples that are nearly identical to each other, and then they have two solutions to one of the one of their examples that are also nearly identical. And so these signatures are kind of simplified from what the book uses. It uses so in the book they use a mutable map instead of the environment lookup thing here. But otherwise it's basically the same idea. So two interpreters for Boolean expressions. One of them is evaluate, which given an expression, a Boolean expression, and an environment in which we can look up variables, right? Variables named with strings, and that could give us Booleans. Then we can interpret the entire expression into a Boolean. But also, there's another interpreter which, when given a Boolean expression, E, and an environment in which we can look up expressions, then we can get an expression where the variables are replaced with sort of the reference, right? But the variables don't have to be strings, right? It's the same as before. So we can actually write this, the structure of this interpreter sort of once and for all. So instead of using strings, we'll just use generics, and we'll say that variables are represented by some type A, right? We have something embedded that represents variables, and that the type that represents variables is A. Okay? So then we can write a fold, a generic interpreter over these Boolean expressions, and then we just take a handler, we take a visitor, right? We take a handler for each of the instructions, and the one this is essentially the same as the one for the string example, with the difference that there's a lookup function for looking up variables of type V and matching them up with A. Okay? So then, once we have this sort of generic, we can write the two interpreters just by calling fold with different arguments. So the first one evaluates to a Boolean using an environment that maps variables of type A to a Boolean. But the second one returns the same expression that it got, except with the variables expanded to their bindings in the environment. Does that make sense? Everybody see that? So we're folding and we're saying handle the literal. In the first case, we're saying handle the literal just by returning the Boolean. Oh, actually, that should be env, not identity. It should be looking it up. No, actually, the expression contains literal Booleans. Sorry, literal Booleans. So we fold, and for literal Booleans, we say identity. For and, we say and. For not, we say not. For or, we say or. But for variables, we say env. Look them up. Look up the Boolean in the environment. Now in replace, we just pass in the constructors of the algebra, so we'll get exactly the same structure out, except in the variable case, we'll have expanded it out to an actual expression. But wait a minute. Look at the type signature of replace. Does that look familiar to anybody? Yeah? Look at it. Look at it some more. It's flat map, right? And so once you see it, you're just like, wait a minute. So the Gang of Four book, the bastion of object-oriented programming, contains monads, right? So the interpreter pattern is essentially the monad pattern. In fact, let's look at the structure of interpreter again, right? So we have an abstract expression, and then we have a terminal expression, and we have a non-terminal expression which is recursive, right? So why do we need a pattern language at all? Can we just model this in Scala? Yes, we can. So we don't need, we don't need English. We can just say, use a higher kind of type. And so you have some abstract expression, right? Sealed trait, an expression. And then a terminal expression carries some value of type A. And you have a non-terminal expression then that adds some structure of type F. And that structure is then full of other expressions, right? But this is actually a very common data type, and it's called the free monad, right? So interpreter is essentially the free monad pattern, right? So who would have thought that like free monads were in the Gang of Four book? And this structure is in Scala Z, but it's it's easy to write on your own. Okay, so then the Boolean algebra that they develop in the C++ implementation could look like this. You have a seal trait, boolalg for Boolean algebra, and then you have these cases. So you have a literal Boolean, and then the and, or, and not cases just contain a. They just have holes in them. But because the idea is that boolalg is going to be the structure that contains then the recursion, right? So in the case of and, it has two holes. So that says that we're actually going to, if we go back to the free thing, we see that that f is not going to be boolalg, and if it's and, it's going to be two expressions, right? And if it's not, it's going to be one expression. And so then the Boolean expression language is just the free monad generated by the Boolean algebra. All right, so what does it mean to interpret an expression in the free monad? Well, it means to translate it to some other monad. So this could be the sort of side effect monad, or it could be the IO monad, or it could be state, or it could be option, or it could be list, or it could be any other monad or any other data type that has the same structure. Basically, that has some terminal expression and some non-terminal expression in its language. Okay? So yeah, monad is just something very simple. So a monad has pure and bind, which you can see as the terminal expression. So that is water. Should have held on to that mic stand. Okay, so then we have a terminal expression which is pure, and then a non-terminal expression. You could see that as being the bind case. So it's, you have an M full of A's, and then you have a way of turning your variables of type A into M's. Right? And then the squiggly line thing. So if we look at the fold map signature, it's saying. Yeah. So it's saying that if we have a recursion over this F thing, we can turn it into, we can translate it, interpret it in the language G by turning all the F's into G's. And that's what that squiggly line thing is. It turns an F of A into G of A for any A. We can implement the option monad using free, just by using sort of a trivial functor. So we turn off the recursion. So then we have either an A or unit. And we can construct any kind of language that we like. So more or less any problem that we can think of can be modeled as an algebra like this. And then we can take the free monad that turns that into a recursive expression language with variable bindings. And here's one I made earlier. So this is one I worked on with Dick Wall and Jessica Carr. And so we made this free monad to talk to couch. And so we just have an algebra that has like one case class for everything that you might want to do to a couch database. And then we take the free monad of that, like that. We have a couch monad. And now we can talk about couch things in our little language. But what that means is then given by an interpreter like this. So run couch takes that thing and turns it into like a Scala Z task or an IO monad or side effects or something. So in summary, I think that the Gang of Four book, if there's anything to take away from this book, it's that composition should be favored over inheritance. And I think that they try to hammer that home here a lot. And they also say to prefer immutability over mutability. They don't necessarily say that strictly, but that's basically what that means. So instead of having a superclass with inheritance where you model the different behaviors as concrete subclasses, you have an algebra and you model the different behavior or the different meanings with different interpreters. That's all I got. Thank you.